starting to look at the previous homework submissions, homework 0. And just a few points I want to make. Most people turned in reasonable documents, but there's a few cases where, let's say, the rules were not being followed. So I just want to make a few clarifying comments about homework submissions. So everybody's homeworks should be compilable into a single document, so HTML or PDF document. But your source should all be in either RMW, which is the SWE format, or RMD, which is the R Markdown format. Okay. So things that we were seeing were multiple files, so like a different file for different questions. That's not what we're looking for. We're looking for it all compiling, so we don't have to compile multiple files. Let's see what else do we see. I think people were submitting a LaTeX, .tex file for the written part of it, and then an RMD file for just code at the end, and kind of splitting it that way. Don't do that. So I have the option to submit a tex file, but only if you're including it inside of your R Markdown file. Okay, so you can like if you need like a preamble to your contact code, you can include it at the beginning and the header of your RMD file. But here's the rule of thumb: if we can't load your RNW or RMD file into RStudio and hit compile and then see your nicely formatted report, then you're not submitting it in the right format. So that's kind of the rule of thumb. Make sure you can just load your document. Even if it includes an external file, that's fine, but it should just kind of compile right down RStudio and give you one report. You won't be chasing files all around and figuring out how to compile different formats and everything like that. Okay, so that's and yeah, so some of you that have multiple files will be getting a message from the TAs, a comment in the Canvas to resubmit your homework into a single format that we can use. So if you get that comment, just reformat your answers and resubmit. And we won't take points off it, just resubmit the same answers, just format it correctly. The other point I want to make, and this is for everybody, some people are doing a better job than others, but in general, the goal of using kind of the R Markdown or Sweeve is that we're writing readable code. So you're supposed to have it's supposed to be human readable. so it's not. So I don't want to just dump your code and it'll print out the plots and everything. You're supposed to mix it in with text description of what you did and what the conclusions are. Okay, so it should be readable. Like I should be able to sit there and read it and understand what you did. Okay, so it should look nice and formatted well, but that's usually pretty straightforward in our Markdown and so forth. But the point is, we don't want just like hard to read code just that we can't understand. This is going to become more important as we go on. These first exercises are pretty simple. But as we go on, you're going to be writing more and more complex code, and you're going to need to do more analysis in terms of like describing what you did and what you learned and that kind of thing. So just keep your kind of eyes out for writing readable documents, nice professional-looking reports. So you will be, I think the first report, the first homework is not a big deal because there wasn't much code. But as we go on, that will be part of the grade. Is it really, well written and explaining what you did properly? Okay, so that's kind of something to watch out for. Any questions about that? Or anything else for that matter? Okay. All right, great. Okay, so let's I'm gonna maybe review where we are here. So we've been talking just kind of in general the past couple of weeks or so about how to put priors on distributions. And so we're in this Bayesian setting, just to remind everybody, we've been talking about a posterior distribution is what we want to do in order to do Bayesian analysis. So we have some parameter theta. X is our data that we're going to observe. And we want to make some type of inference about theta given the data we observe. So that's whether it's a mean Gaussian or the probability of a Bernoulli or what have you. This is kind of what we're working with. And of course, Bayesian tells us this is proportional to a prior probability in theta or a PDF or PMF times our likelihood, the probability or density of our data given the parameter. And so yeah, so basically we've been talking, focusing on this question of, well, what do we do with, how do we come up with a proper choice for P of theta prior? And we've seen a couple of different approaches so far. One approach we saw early on was just use uniform on theta, which may or may not be a valid probability distribution. We saw with the Bernoulli, where theta is a probability between 0 and 1, you can very easily find a uniform distribution between 0 and 1, and that all works out fine. With the principle here of why we choose uniform is that we don't want to favor any particular theta a priori. We don't have, if we, for instance, have no reason to expect one theta versus another, we just say, let's use uniform. And this was, in fact, what we said Bayes chose in the original essay he wrote, and also Laplace independently kind of discovered for Bernoulli, or kind of came up with the idea of using a uniform prior on Bernoulli theta probability. The second kind of principles that we came up with were conjugate priors. And just to remind everybody, that was when we had our likelihood in an exponential family. So remember, that's when P of x given theta is something proportional to some, some function of x times the exponential of some sufficient statistic times some what we call the natural parameter eta theta. So it's where we had basically you have e to the something where the something splits into multiplication of something in terms of x and something in terms of theta. No other interaction between x and theta. So we had this exponential family. What we saw was in these cases, we can come up with a P of theta such that when you multiply it by something of this form, the posterior distribution is in the same family as the prior distribution, right? And remember, the simple example of that was the beta distribution is conjugate to the Bernoulli distribution, and the posterior of beta Bernoulli is again a beta distribution. We also saw that in the continuous case, likelihood case, where a Gaussian with a mean parameter, but kind of set the variance to be fixed, the conjugate distribution is again a Gaussian on mu. And then the posterior is again Gaussian. And we saw the properties there where conjugate priors basically can be thought of as pseudo observations So if you have previous experiments or data to work with from, let's say, published data somewhere, published experiments, you can incorporate that prior experiments into a conjugate prior. Is one way to do it. One way to use conjugate priors. Then last time we started to talk about non-informative priors. I should mention uniform on theta is, again, that does make sense. It can be thought of as a non-informative prior in some sense. It's some definition of non-informative. As we're going to see today, there's another definition of non-informative in addition to the one we saw last time. The last time was maximum entropy. So in some sense, we have, after the day, we'll have basically 3 definitions of non-informative. So it's not a clear-cut, only one way to call something non-informative. So you could say this is, you could argue that this is non-informative, saying something is uniform. I could also argue that the max entropy principle is my non-informative prior. As we saw, max entropy sometimes leads you to a uniform distribution. Remember the idea behind max entropy last time was that the entropy of the probability distribution is how spread out, how basically uniform is the distribution. And so we typically have some type of constraints on our theta parameter. So for instance, in the Bernoulli case, we have the constraint that it's theta is some number between 0 and 1. We want to keep that as a constraint. In the exponential distribution, we know lambda, that parameter is between 0 and infinity, so it's positive, that's a constraint, yeah.
Something I wasn't quite with that I confused on. When you impose a constraint with posterior probability, also appear to that constraint?
It depends on the constraint. So yeah, good question. If your constraint is that the support of the distribution is between, say, A and B, where A or B might be minus infinity plus infinity, but let's say you constrain it to be somewhere in some range, then if your prior adheres to that support, then your posterior will also, because if the support of theta, if it gets zeroed out outside some range in the prior, then the posterior will get 0 probability outside that range as well, just because of this multiplication here. So that type of constraint, yes, if you constrain here that way, the posterior gets constrained. Now, one caveat, of course, if you find that you observe some data such that your likelihood gives you some non-zero values outside this range constrained by your prior, then it might be the case that you should either rethink your prior or rethink your likelihood function. So if you have some strong likelihood of being outside the range of your prior, that might be a bad sign, that something wasn't chosen correctly. Not necessarily. Sometimes you really do want to fix that range. Now, the other type of constraints we talked about in max entropy, that they do not carry over from prior to posterior. So for instance, we talked about, with max entropy, we talked about constraints, of the expected value of some functions. So let's say I had some function f sub j of theta was equal to some fixed value c sub j. So these were constraints. So these were, we wanted to constrain the expected value. Now this expected value, though, is expectation under just theta. So it's expectation, in other words, it is the integral of fj of theta times the prior p of theta. This was just a property of the prior distribution, expectation of the prior distribution. I want that expectation to be equal to some value. Now, if case for the prior, that's not necessarily the case for the posterior. Once I throw in the likelihood, I might get a different expected value. This constraint may be broken in the posterior. So if we just to kind of as a thought experiment to convince ourselves of that, think about the Gaussian. We saw that the max entropy prior for the mean parameter mu was what? Wait, sorry. I should have said if I constrain the expected value and the variance, so expected value of mu and expected value of say mu squared, what would I get as a max entropy prior? Yeah, Gaussian. So really for any theta, I've said mu, but really for any theta, if remember, one example we looked at is if I put two constraints, expected value of theta equals, let's say C1, and expected value of theta squared equals C2, where these are just some constants. I don't really care right now what they are. This set of constraints gives me that theta has to be Gaussian with some mean, let's say mu naught, and some variance. Because remember, these constraints lead us to p of theta being proportional to exponential of just inside here I just have the sum of these constraints. So remember, if my f's are just identity and the parameter squared, then I get a quadratic inside the exponential. And remember, sorry, this should be times some lambda j's that make this thing work out. And of course, there's a normalizing constant. So remember, if I have a quadratic inside an exponential, then it has to be Gaussian, right? That was our argument a couple lectures ago. So anyway, so getting back to, so if I have, for instance, the max entropy prior on, let's say I'm looking at theta is the mu of the Gaussian, the mu parameter of the Gaussian, then that says that mu is also, let me switch my notation here. So let's say I'm talking about mu here. If it has, I know this is C1 here, and let me be a little bit lazy and just say I'm gonna fix the variance instead of the theta squared. If I say I'm gonna put the constraint that the variance of mu is equal to C2, then I would get this, right? I would have to pick lambdas here so that I get the Gaussian C1, C2 here. Okay, so, but coming back to, I'm still answering your question. So if I were to use this max entropy prior, then this max entropy prior says, I basically fixed two constraints, that my parameter mu had a particular expected value and had a particular variance. If I fix those as my only two constraints, it's a random variable on the whole real line, then maximum entropy says the Gaussian distribution with that mean and that variance is the maximal, it's the most spread out distribution that you can get in terms of entropy. with these two constraints. Okay, that's what we kind of showed last time. Now, P of mu will be this, and it'll have those constraints, these two constraints. But we know from the Gaussian example when we did conjugate priors that when you then add likelihood, the prior and the likelihood combined to the posterior, that also gives you a Gaussian in mu for the posterior, and that, but it has a different expected value and a different variance, which is a kind of a compromise between the prior and the likelihood, right? So you can see that the constraints we put into the prior here in the max entropy distribution don't carry over to the posterior. So long answer to your question, but yeah, that's just an example. Okay, so to call these constraints, just be clear, you're not really constraining. In this case, you're just constraining you're trying to constrain the prior. It has certain properties that may or may not make sense. If you have some reason to believe that these should be the properties of your prior, that's what you use. Okay. Okay, so today what we're going to talk about is the final non-informative prior called Jeffrey's prior. I should say priors, depends on there's a whole set of priors, but the principle. To begin, to define priors that are under some definition as non-informative as you can make them. And we'll see what that means here. Okay. Before we get into that, any questions about this, just reviewing kind of what we've gone through so far? Okay. Right. So what is a Jeffrey's prior? So the first thing I want to do is motivate why, if we've already got maximum entropy as the definition for non-informative, why do we need another definition of what a non-informative prior is? So let's come back to the case where X is Bernoulli with some probability theta, and then the max entropy prior, if I don't have any constraints on theta other than theta is between 0 and 1, what was the max entropy for theta? It's just uniform, right? Because then I've got no constraints here, so I've just got a constant PDF. So it's e to the constant. So in the Bernoulli case, this was the same as our first thing that we did at the very beginning, which was uniform theta. Max entropy is uniform. Okay. So that is the max entropy for theta. Now, if you remember from conjugate priors, I could also talk about the natural parameter, let's call it eta, instead of theta. Now, who remembers what that was equal to? Yes. Yeah. It's the logit or logit or logit or however you want to pronounce it function of theta, which is natural log of theta over 1 minus theta. Okay, so the log ratio, log odds, or logit function of the field. Okay, so now the question is, well, we saw with conjugate priors that eta is a perfectly good parameterization of my Bernoulli distribution. I can use it instead of the theta parameter. I can use this eta parameter, right? And get the exact same deal here. because all I'm doing is writing the Bernoulli in exponential family form, one way or the other. It's the same distribution. Okay? So now, what if we say eta? Oh yeah, first of all, what is the range of eta? Say again.
Unbounded?
Yeah, it's unbounded, right? So this can go from minus infinity to infinity, right? As the log, as this thing on the inside, this is a fraction, it's a positive fraction, but as it goes to 0, this goes to minus infinity. As this theta gets, 1 minus theta gets close to 0, you go to infinity, right? So this is unbounded minus infinity to infinity. This is, I should say, in the range, minus infinity to infinity. So I've got now a parameter that is on the whole real line, and I still want to say it's unconstrained. There's no expected value constraints on it because I wasn't putting expected value constraints on theta. And in that case, then eta, really the max entropy distribution, is going to be, again, uniform on minus infinity to infinity. As we talked about last time, that is, of course, not a real probability distribution. So P of eta, so if eta is uniform on minus infinity to infinity, that would be the max entropy distribution. It turns out to not be a probability distribution. That is not necessarily a bad thing if, when you combine it with the likelihood, you get a valid posterior distribution. Okay? But what we see here now is, and we'll see in a second, that this does lead to a valid posterior typically if you have more than 1 or 2 data points. But what we see here is I've got 2 different possible max entropy distributions, and all I did was reparameterize what my Bernoulli, just the function, the form of it. It's the same distribution. I just reparameterized the parameter theta to give me eta. But I should have the same distribution, and so the max entropy principle, we would like it to give us the same prior. But it turns out that it may not be obvious yet. We'll prove it here in just a second. But these are actually 2 different priors on our Bernoulli distribution. Okay? So can anybody tell me how would I see that these are actually not equivalent to each other? This theta prior and this eta prior. I'm asking everybody lots of questions, see if everybody's paying attention and improve things here. So how would I test? Yeah.
First of all, if you were to integrate that, it wouldn't integrate to 1, would it?
That's true. Yeah.
So it's not a proper distribution.
Yeah. Okay. So one quick argument to see why it's not that's a good point. Is one quick argument is, well, this is an actual probability distribution. This is not a probability distribution. So there's no way they could be equivalent. And that's actually true. That's actually a quick way to see it. Yeah. I was going to do it the hard way, but that is an easy way to make that argument. Can anybody tell me? Let's say this did integrate to 1. Just bear with me here, just for devil's advocates. Let's say this did integrate to 1, and I had 2 different priors in 2 different parameterizations. How would I see if they're equivalent to each other or not? In general, let's say I have just some theta parameter and I reparameterize it to eta. How can I tell? Put a different distribution here. How would I tell if they're equivalent or not? I'll give you a hint. It's using computation that you did in your homework 0 that you've already turned in.
It's the change of
exactly, change of variables. So if this is just a change of variables of this random variable, and so if these distributions are equivalent, then applying the change of variables formula to this PDF should give me this PDF, right? That would be the way to test if they're equivalent or not. So if this PDF is just a change of variables of this PDF, then those are equivalent distributions. Otherwise, they're different. Okay, so that's another way to look at this. Yeah, so, but that being said, you don't actually have to go through that, because if I do a change of variables of something that integrates to 1, I still get a PDF that integrates to 1, right? Just because I change variables doesn't change. That's what the whole change of variables does, right? Is it makes it integrate to the same thing. And so if I change variables and don't integrate to 1 anymore, then it must not be a transform of this. Okay, so the eta, uniform on eta is not the same prior as uniform on theta. These are two different, the one's not even a distribution, but they're two different priors. Okay. Right, I won't do the change of variables, but if you do the change of variables of eta back to theta, okay, and this, by the way, is the inverse transform, right? This is if to get from theta to eta, right? So I'm trying to go this way. So this is the kind of your kind of G inverse or whatever. Then what we see is that this is equivalent to the probability, the prior on theta that looks like, I should say proportional to, because it doesn't really, again, this doesn't integrate to 1. So if you do the change of variables, which I'll save you, or I'll spare you the math, and if you wanted to do it yourself, it's easy to do. You just apply the change of variables formula to this inverse function. You get transform eta back into theta. You get that p of theta, that this uniform on eta is equivalent to p of theta being 1 over theta times 1 minus theta. Okay, so it's definitely not uniform. And if you plot this between 0 and 1, you get kind of these asymptotic type things. It kind of flies off to infinity at 0 to 1, like that. So this is the distribution that is uniform on the natural parameter eta. So, long story short, is the maximum entropy principle has actually not given us a unique answer to what is a non-informative prior for the Bernoulli distribution, right? Because if I choose theta, which is what we typically use anyway, I get one distribution, which is just uniform 0 to 1. If I choose the natural parameter eta to describe my Bernoulli distribution instead, and say I want to use the maximum entropy principle, then I get this prior distribution, which, if I rewrite it in terms of theta, looks like this. Okay? Yeah, so by the way, notice that we know the likelihood, if I have x1 through xn given theta, that is, I should say proportional to, or no, it's actually equal to theta to the k times 1 minus theta to the n minus k, where k is just the sum, right, of the x's. And so if I multiply that times this prior, then my posterior, given the x's, is proportional to, these are just theta minus 1, 1 minus theta minus 1. So this is proportional to theta to the k minus 1, and 1 minus theta to the n minus k minus 1. And this thing will be a proper probability distribution as long as k is bigger than 1, or greater than equal to 1, and as long as n minus k is greater than equal to 1. So as long as I've flipped at least one heads and one tails, this is a proper distribution. Okay, so long story short, there's a problem with the max entropy principle in general. If you care about my prior distribution, shouldn't really matter how I parameterize the the parameters to my likelihood.
I have a question.
Yes, go ahead.
So, the theta and eta both are completely different variables. One is a bounded one and one is
Yep.
unbounded.
Yeah, well, we should be careful, yeah, they're completely different, but they're the same, they're just reparameterizations of one another.
Yes, so
yeah.
finding a maximum entropy for theta or eta, there might be different situations.
Yeah,
So why is that completely bad that they
that
get
they're not the
different?
same. Yeah,
Yes.
well, okay, so if we think of the philosophy of max entropy says, I have a likelihood which has some parameter, I'm going to put a prior on that parameter. The best prior, if I have no other information about that parameter, is to make it as maximum entropy or least informative as possible, which basically you have no constraints means make it uniform over its range, as we see in this theorem here that we did. The problem is that if I reparameterize the parameter that goes into my likelihood, I don't change the likelihood. So I'm still modeling my data exactly the same way. I still have a Bernoulli, in this case, independent Bernoulli trials for my data. And there's no principle to tell me you should parameterize a Bernoulli with theta versus the log ratio of theta there. So either one is the exact same explanation of my data, and if the only principle I have is that I want the least amount of information into the parameter of that likelihood, this gives me multiple choices that are not the same. And so maybe if you had some type of guiding principle that said you should always parameterize your likelihood this way or should always parameterize your likelihood that way, then you could argue if I always parameterize my likelihood this way for some reason, which I can't think of the reason I always parameterize the likelihood one way or the other, then you could use max.
To favor unconstrained optimization.
Say that again?
If we want unconstrained optimization, we do not want. Because theta.
Then you don't want theta between 0 and 1.
Yes.
But okay, that's fine. But then I can choose a different transformation. I can do arc, like hyperbolic tangent, and get, I think, or something along those lines. There's lots of different transformations that take me from 0, 1 to minus infinity to infinity. And so I'll get a whole other prior distribution for max entropy in that case. So yeah, I think no matter how you slice it, there's never, that I can think of a case where you would prefer absolutely to have one particular parameterization of the likelihood in terms of the parameter of that likelihood function and no other parameterization. And so in that case, the maximum entropy principle is a little bit tricky to use because it doesn't agree with itself over reparameterizations. Okay? So that's where we are. Any other questions at this point? Okay. So this, brings up a good, philosophical question: is there really a way to say we want to be as least informative as possible? We want to be as uniform and not favor or bias our choice of our parameter theta before we see any data. We want to kind of equally weight all the possible values for theta, while at the same time make it invariant to reparameterizing our likelihood, reparameterizing the parameter theta. Okay, that's the question, and it turns out that that's what we're, if you couldn't tell, that's what we're going to do with Jeffrey's priors. So we're going to try to have a similar principle as max entropy. So be as spread out as possible, but correct this problem that we are not invariant to reparameterizing our prior. Okay? And, right, so to do this, we first need to define something called the Fisher information. And by the way, if you look at the website and schedule page for today's lecture, this is another one of those cases where Wikipedia is probably the best source for everything you ever want to know about Fisher information, so there's a link to that Wikipedia article for Fisher information. So Fisher information is the main ingredient going into Jeffreys prior. Has anybody come across Fisher information in statistics? Okay, a couple of people. Okay, so Fisher information, which I'll try to write as a cursive I, but probably poorly, of a parameter theta is based on just our likelihood model. So, so up here, just our P of x given theta. And what it's going to look like is the expected value of the square of our log likelihood function. Or sorry, our gradient of our log likelihood function. So we take the derivative with respect to theta of the log likelihood function. So remember, the log likelihood function looks like this. I'm just going to have one x here, so just one data point. And we square this. We take its expected value. This is an expected value over x. I should say really given theta. Okay? So this expected value is over x. Okay, so this looks really complicated. Let's see. So I think maybe some examples would be good. Let me actually, before we get to an example, let me give kind of an idea of what Fisher information is telling us. So the derivative of your log likelihood function, this thing inside of here, not the square, but just the thing inside the square, this is called your score function. Okay, and if you're going to do maximum likelihood estimation on a computer, and you don't have a closed form, like we know maximum likelihood for a Gaussian mean is just take the sample mean of the data. We don't need to do any crazy computations. But if you don't know a closed form, then the score function is very often how you solve maximum likelihood problems. Because this is just the derivative or gradient of the log likelihood. You want to maximize it, so you just can do a gradient ascent. So this would be like this is what you would use to do gradient ascent. We would compute the gradient and step in that direction to maximize this likelihood estimate. And again, this is gradient in theta because we're trying to maximum likelihood. We're trying to maximize this over theta. Remember? So that's where one place where this thing called the score function comes up, and you can imagine that if this data point x, so this is inside here is just for one data point x, one, let's say, not with, let's ignore the expected value for the time being. If the data point x is telling me very strongly you need to move in this direction to get the best theta, then x is giving me a large derivative of the log likelihood function. So the score function is, in some sense, how strong a piece of information is this point x giving me about my log likelihood theta. Okay? And now what we're going to do is we're going to take the magnitude of that information, that gradient information that x is giving me, and we're going to average it over all possible x that we could observe. So the Fisher information is in some sense the average, what's the average squared score here, but it's the average amount of information data could give me about theta in terms of log likelihood. Okay, so that's intuitively one way to think of the Fisher information. Okay. Another place, let's see, another place Fisher information comes up is if, this is just a side note, but just to give you an idea of why Fisher information is important, is if you have theta hat as an estimator, and this is back in frequentist statistics, so like a maximum likelihood estimator, for instance, but theta hat is an unbiased estimator. Of theta. So it's some statistic you compute from your data to estimate theta, and it has zero bias. Then there's a theorem called the Kramer-Rao bound, lower bound, which says that the basic conclusion, I'm skipping a lot of details, but the basic conclusion where Fisher information is important is that the variance of this statistic you computed is bounded below by 1 over the Fisher information. So this tells you that if you want an unbiased statistic to estimate theta, you're kind of stuck with this much variance in that statistic. So you can't get, a statistic that's any more precise, any more, tightly distributed than 1 over the Fisher information. Okay. Now, we're going to see in a minute. We're going to look at some examples and see that we're going to be able to see a few cases where you hit this lower bound exactly. But anyway, that's another importance of the Fisher information. It's telling you if you're, no matter how you choose this statistic, you can choose any statistic you want, and if you want to make it unbiased, you are stuck with some type of uncertainty, this amount of variance in that statistic. Okay, so anyway, that's the Fisher information, just definition and a little bit of motivation for why it's important, but now we're going to see why it's important in terms of priors. Well, let me just define the Jeffreys prior, and then we'll just go through a few examples. So the Jeffreys prior, using the Fisher information, we're going to set our prior on theta, so our P of theta, to be proportional to just the square root of the Fisher information. Okay, and that's it. That's the Jeffreys prior. So this all seems very mysterious probably at this point. Why the heck do we do just the square root of the Fisher information? And but yeah, we'll talk about that in a second, but let's just take a look at, I just want to make one point really quickly. This Jeffreys prior depends, I mean, you see here, it looks like there's no likelihood in here, but it does depend on the types of, the family of likelihoods that you're working with, right? Because the likelihood function came into the definition of Fisher information. So if I change the likelihood function, I say I'm going Gaussian, and I change to like Cauchy distribution or T distribution or whatever else, that would change the Fisher information and change my prior. So yeah, so the point is that this is specific to, you pick a particular class of likelihoods, just like we've done for conjugate and max entropy and everything else, and then Fisher information tells you what the Jeffreys prior would be. Okay. So why this form for Jeffreys prior? Why is this what we're going with? It turns out that under certain kind of continuity assumptions, regularity assumptions on your probabilities, the Jeffreys prior is the only prior which is invariant under reparameterizations of theta. There's no other choice of prior that would work. Okay, so if we want that principle that we said at the beginning, that we want to be able to reparameterize theta, or reparameterize the theta, whatever our parameter for our likelihood is, and not change the prior, then Jeffreys is your only choice. Again, under most ordinary kind of parameters we're talking about. Yeah.
I theta is, in this case, a random variable, not
Yeah.
a distribution, correct?
So theta is a random variable. Yeah, and yeah, in this case, I of theta is kind of just a function of theta, of a parameter of theta, right? And so this is defining like a PDF of theta.
So I of theta in this case is PDF.
P of theta is a PDF in theta, yeah, the prior PDF, yeah. So I'm being, yeah, kind of, let's back up a second. So I'm being, throughout the class, just as a reminder, I'm being fast and loose with notation. So when I say like P of X, it means, something, let's say, something like proportional to, like say if we're doing Gaussian, I would say something like this. Right, I would write the PDF, but I'm also, so X is really just a variable that defines the PDF, but we've also been saying X is the random variable, and also X could be possibly an observed value of that random variable. So we're kind of overloading notation here. So yes, so a good point to make here is that in this case, theta is like the variable that's defining these PDFs, and I'm taking, it's like just a variable inside a function, basically. It's a deterministic thing inside this function. I'm taking derivatives with respect to that variable, as I would usually do with a PDF. But I'm also thinking of theta, like, in this notation, I'm thinking of theta as the name of the random variable, right? Which is technically different from the theta that's inside the PDF. We could, like, if we wanted to make a distinction, we could do things like, capital X is this random variable, and this random variable has this PDF kind of thing, where if I use lowercase x's. But anyway, I'm using notation because I don't want to have to distinguish capital thetas from lowercase thetas. Is one reason. But yeah. So yeah, but this is everybody clear on the question?
So this distribution is kind of characterizing it on average for a particular location, how much variation is there in likelihood with respect to theta parameter?
Yes. How much? So one thing which I don't think we'll prove because we're going to run out of time, but I'll give one property here is that the expected value of the score without a square in it is 0. Okay, so this actually is equivalent to the variance of the score. So it is the variance of the law of likelihood. Where again, this variance is variance in X. Okay, so yeah, so it is sorry, I forgot the derivative again.
variance in X given theta, right?
Yes. Because now, in this frequentist case, because Fisher was the kind of grandfather of frequentists, all of this was theta treated as a constant. But when we use it for Fisher information, for Jeffreys prior, of course, theta is a random variable. But yeah, because the expected value of this is without the square is 0, then the e of x squared is the same thing as the variance, and so to answer, I think the way you said is correct, that the Fisher information is telling me the variability of the score function, or the variance of the score function, which is the variance of the derivative of the law of likelihood. And so the Jeffreys prior is really the standard deviation of the score function, the standard deviation of the information that that theta is getting from some x's. Yeah.
So what is the significance of this information? Like this is standard deviation, how it can be useful as a prior?
Yeah. So basically, one way to think of this is that there's two motivations. One is that, as I said, it's the only way to have a prior that's reparameterization safe. You can reparameterize and don't change your answer. But you can think of this as, again, it's the most, well, it's the only one that's that you can reparameterize, but it's also, in some sense, it's also as uniform as you can possibly get. But that sense is hard to, that argument's a little hard to make, but it's, let me see if I can explain this a little better. Yeah, I think if we look at some examples, it'll be a little more clear how this gives us what we would hope to see in terms of uniformity for some examples that we're familiar with. Is probably the easiest way to see it. But the statement I was trying to make, which is a bad statement, that's why I stopped myself, is this uniformness you can get and be reparameterization independent, but it's the only thing you can do be reparameterization independent. So of course it's the most uniform you can get. So anyway, so that's not a good argument for why it's not informative. But I think let's do some examples and see here. Okay, so I think let's do the simplest example we can do probably is the Gaussian. So, and then there's going to be a connection, by the way, of Jeffreys priors back to conjugate priors, and we're going to see how it's. In fact, let me give you the punchline. It'll help explain why it's as non-informative as we would like. So conjugate priors, it turns out, if you look at conjugate priors and you take the parameters, so for instance, the beta distribution, and you, for Bernoulli, and you make the parameters go in a certain direction that spreads that distribution out more and more, in the limit, you end up with Jeffreys priors, typically. And so Jeffreys priors are, in some sense, limiting cases of conjugate priors that give you things that spread out as much as you can.
Because Fisher information already has log likelihood in it, so it should be relative. No, but posterior has to come like that.
Yeah, so, well, yeah, exactly. It's because the conjugate prior has no, yeah, that's hard to see why this works, other than seeing examples. I actually can't tell you why that I don't, in fact, I don't think that always, I don't even know if that always holds. That's something I have to check. But we'll see for some specific cases that conjugate priors in the limit give us Jeffreys priors. But you know why from that formula that happens, I can't tell you. To be honest, I don't know why that comes up that way. let's do a Gaussian. That I think will help just make it more concrete. So let's say I've got a Gaussian. Oops, not 0. So again, I'm going to have x, just one random variable x, which is Gaussian. And again, same trick as we did with conjugate priors. This is going to be a random variable, and we're just going to fix this as a constant. Okay, so there's a known sigma squared, just as for the time being. We're going to do on Thursday, finally, mu and sigma squared unknown random variables. But for now, we're just doing one parameter at a time. Okay, so mu is our random variable. We're going to put a prior on mu. The Jeffreys prior for mu, what does it look like? So we first need to compute the Fisher information of mu. Okay, and it's going to look like, yeah, okay, good. The expected value of d, now of course I'm switching theta to mu. Take the derivative of the log likelihood function. This is just going to be a log Gaussian, which you know how to do. A log Gaussian is just, the normalizing constant doesn't depend on mu. We're taking derivative with respect to mu, so the normalizing constant goes away. We just have the thing inside the Gaussian, which I have written up over there. You know, it's the minus x minus mu squared or sigma squared deal. So that's the only piece we need, really. There's a 2 there. Oh, that's a square. And then that whole thing squared. So if I take the derivative of this, I get a 2 canceling out there. I get a minus sign. Change it, minus sign, and then chain rule, and then I square it again so the minus sign goes away. So now I get expected value of x minus mu over sigma squared squared. Okay? Are you happy with that? Now, sigma squared, remember this is an expected value still over x, given mu. We're leaving an expected value over x here. Sigma squared is just a constant, so it can come out of the expectation. It gets squared again, so I get 1 over sigma to the 4th. And then I'm left with the expected value of x minus mu squared. And where does that leave?
Variance.
Yeah, it's just the variance, so it's sigma squared, right? It's just the variance of the Gaussian. So I get sigma squared over sigma to the 4th, which is 1 over sigma squared. So notice that's my Fisher information. I don't know how people write on this board so that it doesn't actually erase fully somehow. So my probability of mu, my prior distribution on mu, is proportional to the square root value, which is 1 over sigma. Now, proportional, as far as we care, sigma is just a constant in mu, so we don't even care what that is. Whether it's sigma or 10 sigma, it's just some constant. It's proportional to this, so it doesn't matter. So that says we're really just constant in mu. So I might as well just say this is proportional to 1. In other words, it's uniform distribution in mu, which again is not a proper n-rate to 1 probability, right? So we get, in some sense, as again, it's actually the same thing as the unconstrained max entropy solution in this, for this particular instance, the mean parameter of the Gaussian, you get the uniform in mu. And so it turns out that uniform in mu is the only distribution that's going to give us reparameterization of mu independence of our prior. Okay, so this one is maybe not the most exciting because we already came across this with max entropy, but it does at least let us use this prior for mu, and it doesn't have the problem that the Bernoulli distribution had, the max entropy for Bernoulli had. So the max entropy for Gaussian mean, it's okay to use it. It's okay because it can reparameterize. Okay. Okay. Let me, actually we didn't show, there's a lot of things I want to do. I've only got 10 minutes or so. Let's see. Any questions about this example? I'm going to show really quick. I didn't actually show that this thing is invariant to reparameterizations. I want to actually show that to convince everybody that it has the property, most important property I've mentioned. But this is an example, the first example of how this really is, this does give you non-informative priors. And I mean, I think the way I think of Fisher information is it's kind of the amount of information you're stuck with, both in the case of being parameterization independent, but also you're kind of averaging the amount of information that data would give you about theta. And you're kind of stuck with that amount of information being in theta. You can't get less informative in some sense. I know that's a wishy-washy argument, but that's kind of the way I think about it. And you also see it's kind of similar to why that comes up in the Kramer-Rao bound, because it says you can't really get, more precise than one of the Fisher information. Speaking of the Kramer-Rao bound, notice that 1 over sigma squared is exactly the variance of, in this case, if we have just one data point, theta hat is that data point, right? The mean of that data point is that data point. If we're going to do the unbiased estimate of the mean statistic, we take the sample mean. And so the variance of x is actually equal to 1 over the Fisher information case, Fisher information from mu in this case, which was 1 over sigma squared, or if you wrote that, it's sigma squared. So notice in the Gaussian case, I've only done one data point here, but in the Gaussian case, you hit the Kramer-Rao bound. It's as tight as you can get. So the means, and it's easy to see if I did this with n data points, because this is a variance of independent things, the variances add up, right? So if this was the mean statistic of n things, the Fisher information would give me would be n over sigma squared, because I would just take, I'd add up the Fisher informations from n different things, I get n over sigma squared, and so the inverse of that would be sigma squared over n, and that is the variance of the mean statistic, right? If you remember your statistics. And so the Gaussian, this again is just a side note, this is not having to do with priors or anything. Just a side note of the Kramer-Rao bound, we see that the mean statistic, the sample mean statistic, x bar, average of all the x data, is equal to the 1 over the Fisher information. So it hits the Kramer-Rao bound exactly. So that tells you that the mean statistic can't be improved upon. If you want an unbiased statistic, you can't get one more precise than the mean statistic. One thing we're going to see in class in maybe a couple of weeks, depending on how I work out the schedule, is that, just as this is a teaser, is that you can actually improve on the mean statistic. If you want lower variance, you can improve on the mean statistic, but you have to inject bias into it. Okay, and this is an underlying principle of Bayesian statistics, is that priors are injecting bias into your statistic. But you can actually use that to your advantage. And we'll see a case, an example where if you want less variance, you can actually decrease variance, decrease the error in, for instance, predictions by injecting bias into the proceedings. But even for just something as simple as the mean of a Gaussian. Technically, a Gaussian of 3 or higher dimensions, but we'll see why. Anyway, so anyway, that's, again, just a side note. But back to priors, this is the prior we get for Jeffreys prior. So now I want to show that this thing is indeed parameterization independent. Reparameterization independent, I should say. Okay. So let's say I have a reparameterization of theta. Let me get a new part of the word here. So let's say I reparameterize theta with some, of course this has to be monotonic increasing or monotonic decreasing, and differentiable so that I can do a change of variables and take the derivative of it. At least one strict differentiable. Then we know my P of phi basically looks like P of theta, where theta is, theta is equal to, theta is, it's like the inverse of this whole process. It's like a phi. This is kind of like phi inverse, if you will, times the absolute value of d theta d phi. Right, so that's my change of variables where I'm kind of hiding the inverse. The inverse is just theta phi or phi of theta. I'll go the other way. And then I'm just going to plug in the definition for P of theta is the Fisher information, square root of Fisher information. So proportional to the square root of Fisher information here, and then I keep the d theta d phi, change of variables there. And because this is an absolute value, it's like the square root of this thing squared, right? So I'm going to bring this inside the square root, and I'm going to expand out with the definition of the Fisher information here. I get the square root of the expected value of d theta log p of x given theta squared. And I'm bringing in the d theta d phi squared inside. Okay. And right, this term is constant in x, so I can actually bring it also inside the expectation. Right, everybody happy with that? So I bring this inside the expectation. The expectation is an integral, right? And so if I have d theta d phi, and then this is squared inside of here, and a d theta, this is just a change of variables of the derivative theta to a derivative in phi. Okay, so we see that this whole thing is equivalent to the expected value of dd phi of log p of x given phi, and then this whole thing squared. Okay, everybody happy with that?
How did we change from px given theta to x given phi?
Just by doing this change of variables. So I'm just, because phi is just a function of, so if you take dd phi of this, so just think of it as a chain rule. So if I take d theta, let's just say of g of theta, which is a function of phi, I get, wait, no, let me do,
I think we have phi given function.
you only do phi, then I get dd theta of g times chain rule d theta d phi. Did I do this these days? Yeah. Right? So this is just calculus chain rule. Everybody, yeah, I did this step a little bit fast and loose. But this is so I'm thinking of the function g as a function of theta first. So that's this first derivative. But then theta is in turn a function of phi. And so I have to use the chain rule to get a d theta d phi. And so this is exactly, if g is my likelihood in theta, then I get that it's equivalent to this.
Now, in order to do this, you need the transformation to be a one-to-one mapping.
Yes, exactly. So I said at the beginning, this has to be monotonic increasing or monotonic decreasing, so one-to-one, either positive or negative derivative always, and at least differentiable once, because I have to take these derivatives, yeah. So it has to be, just like we had in the change of variables formula when we did that, you have to have, anytime you change a probability distribution, it has to be monotonic, you know, again, with some, obviously weird cases you might do in pieces or something, but yeah, but it has to be monotonic increasing and monotonic decreasing to change a PDF, change of variables. So yeah, we have to have that, right?
But it's that allows us to go backwards on the chain.
Yes, exactly. Yeah, let's just go. We can go either way, right? And so, long story short, this formula here has just switched thetas to phis, and so this is just the square root of the Fisher information in terms of phi. Okay? So if I had started with the parameterization of phi and said, hey, use the prior, which is the Jeffreys prior for phi, I would have gotten the same thing as if I had started with theta and said, hey, use Jeffreys prior for theta. Okay? If I reparameterize phi to theta, or start with theta and reparameterize the phi and use Jeffreys prior on either end, the conclusion is the same prior. So this argument is why Jeffreys prior is invariant to reparameterizing your prior distribution. Okay, so if that didn't make sense to you, again, I will cop out and say, the Wikipedia has this derivation in full glory, same derivation, so it helps to, if this was too fast here at the end to catch it, to think it through very carefully, read the derivation in Wikipedia. And Wikipedia has, of course, lots more details than what I've done here today too. We're going to, on Tuesday, if you want to jump ahead, or sorry, Thursday, I guess today's Tuesday, right? Yeah, Thursday we're going to do the derivation of this same thing for the variance of the Gaussian. And we're also going to do the Bernoulli distribution, which we were stuck on there with the max entropy, gave us two different answers. We're going to get one answer from Jeffreys prior, which is the invariant prior distribution for Bernoulli. Okay, and that's what we're going to do next time. So if you want to jump ahead, that's also all of Wikipedia actually. So